Brownian motion. The price of a stock tends to follow a Brownian motion. Brownian motion is a stochastic process. WT is said to follow a Brownian motion on OT if satisfied the following. First, W naught equal to 0. Second, WT is almost surely continuous. Third, for arbitrary, T1, T2, Tn are mutually independent. Fourth, the mean or expected value EWT is 0. Fifth, the process WT takes on a normal distribution density around its mean. More specifically, the equation is stated. SCHOLES is a single stock with price ST which varies with time. The value of the option deriving from that stock should have a market value that is a function of S and T. dt equal to Vt St. The most significant descriptor of the profitability of an asset is its rate of return. In order to describe the perturbations of the returns on a share of stock, in order to describe the perturbation of the return of share of stock, we will model it a geometric Brownian motion.
Definition: a process takes on geometric Brownian motion if its algorithm follows a Brownian motion. In other words, only fractional changes take place as random variation. Its differential takes on the form as stated below, where A and B are the constant and the function of WT is a Brownian motion. Next, let the stock price take on a geometric Brownian motion, whereas the change in stock price is proportional to the current stock price that is stated as below.
Note that by Ito's lemma, the equation is stated below. Consider an investor who holds a portfolio of the stock and its option, which is PT equal to NYT ST plus N2T dt. The differential is stated below. Maliaris then made the clever argument of holding a ratio of stock to derivative of N1 over N2 equal to negative Vs. This is known as a delta H, so that N1 ds plus N2 Vs ds equal to 0. We are left with dp equal to N2 bracket Vt plus B square S square over 2 Vss close bracket dt, which is completely independent of Brownian motion. There is no dWt term, explicit or implicit.
Let the return dp over p equal to n2 vt plus b squared s squared over 2 times vss dt over n1 s plus n2 equal to r dt. If we rearrange and normalize so that n2 is equal to 1, thus making n1 is equal to negative Vs, we get Vt plus b squared s squared over 2 times Vss dt equal to negative Vss plus Vr dt. For conclusion, Amgren and Melians both serve to elucidate the connection between stochastic processes and financial asset valuation and deepen the insight provided originally by Black and Scholes. The crux of the argument lies with Ito's lemma, which allows one to value an asset whose value is a random Brownian motion function of another asset. While Ito's original formula was developed for more scientific fields, it has found a niche in financial analysis. In their original thesis, Black and Scholes further solved their differential equation with condition that Vts equal to 0 is equal to 0 and Fts equal to maximum 0 s minus e, where t is the exercise state for the option and e is the exercise state indicated in the contract. As a result of the Black-Scholes equation, the application of stochastics to finance has been reinvigorated, and today it has been applied to a plethora of financial assets.